is lower tempo, is going to talk about statistics of veering triangulation.
Thank you. And thank you to the organizers for inviting me and allowing me to speak, and thank you to everyone for coming. So as you can hear, I have a cold, hoping my voice will last throughout the hour. But there's a few experts in the audience on veering triangulations, so if I lose my voice, I'll just go through the slides and you'll just sort of guess. That's what I was going to say. Okay, so first up, I just want to say that really strictly speaking, everything in this is going to be a layered veering triangulation. I'll probably forget to say layered a lot, but everything is going to be layered. That means anything to you, I will say something about that later. All right, so our main characters in our story are first cusp hyperbolic free manifolds. I think we all know what those are. I mean, specifically, we'll be dealing with fibered manifolds. I'll say something about that in a second. And then our other main character is going to be ideal triangulations. This is just a decomposition of our manifold into ideal tetrahedra. And so ideal triangulations are a good way to describe a manifold. We've seen it several times this week. A lot of the software we've been talking about uses triangulations. Like Snappy and Regina uses triangulations to describe three manifolds. So these are very useful, and I personally like geometry, so I would really like it for my triangulation to be geometric. So this means that there's a solution to Thurston's Boolean equations. But if this doesn't happen, then we call our triangulation non-geometric. So another way to think of this is if I have a topological triangulation, I can just try to pull the edges of my triangulation tight to geodesics. And if I'm lucky, everything will work out. But what might happen is, say for example, I have something that looks like that maybe. Maybe these, here's vertices. And maybe these edges are already pulled tight, and now when I pull this one tight, it's going to want to pass through this edge and come over here. And so essentially my tetrahedron has turned inside out. And that's not what I want, but it does happen. So if that happens, then that's an equivalent way of saying that my triangulation is non-geometric. And so if I have this situation where I have a tetrahedron that's turned inside out, the way I can see that, for example, if I have a triangulation in Snappy and I look at the tetrahedron shapes, so each tetrahedron has a shape that is, I can see it as a complex number in this region. So this is a unit circle intersected with the translated unit circle, centered at 1. So they all have shapes in this region of the complex plane. I can normalize it so they all lie in this region. And so if I end up with imaginary part negative, then that's a negatively oriented tetrahedron. Okay? So with this context, the first question that I'm interested in is if I have a triangulation, in particular a veering triangulation, for example, is it possible that some of the combinatorial information for my triangulation can tell me something geometric about my manifold? So a good reason to believe that this might be true is Mostow rigidity, right? Topological and geometric invariants are the same for hyperbolic manifolds, so it's reasonable to try to get topological things to tell you something geometric about your manifold. So that's one question that we'll look at. And then the second one is, as I said, I like geometric triangulations. So the question is, for these triangulations that I'm interested in, layered veering triangulations, how often are these geometric in a probabilistic way? What is the, is a random typical one of these going to be geometric? So that's the other question that we'll address. So first we're going to make some definitions and describe what this triangulation actually is that I've been talking about without defining. So first, some basic definitions of hybrid 3 manifold. I take a hyperbolic surface and a homeomorphism, or I guess a mapping class, and I cross the surface with an interval, and then glue the top to the bottom via the mapping class. I get a mapping torus. And as long as this mapping class is what's called pseudo-Nosov, I get a hyperbolic manifold. So I want to make sure my mapping classes are pseudo-Nosov. And what that means, if you don't know, is very loosely, it means it mixes up the surface a lot. But more precisely, we have transverse singular measured foliations, Fs and Fu. So Fs is the stable foliation, Fu is the unstable foliation on the surface, and a dilatation, so that our map stretches the leaves of the stable foliation by lambda and compresses the leaves of the unstable foliation. So this is a little animation of what that looks like. And so just a remark aside, so these foliations, when I cross with the interval in blue, I actually get a two-dimensional, that's not showing up very well, but a two-dimensional foliation of my three-manifold from those. So this is the pseudo-Anosov, I guess the pseudo-Anosov flow of the map. Okay, so this will kind of come up later, but I'll leave that for now. Okay, so this is the manifolds that we're dealing with. And so to build our veering triangulations, we need to know what quadratic differentials are. Well, we need to know a little bit. I'm not actually going to define them or say too many details about them. But if I have these foliations, a stable and unstable foliation, then there is a unique quadratic differential Q. And Q induces a singular flat metric on our surface with respect to which the leaves of my foliation are geodesics. So, for example, something up here that on my picture doesn't really look square, in the singular flat metric, this is just a square. Right? And then I have singularities. My metric has singularities anywhere where the foliation had singularities. So in this context, we refer to our foliations as the horizontal and vertical foliations, because now we have some notion of horizontal and vertical. And so, so in the context of tight Miller space, our quadratic differential can be thought of as a cotangent vector, or we can actually think of it as a tangent vector, because I want to draw it as a tangent vector. And this is going to be tangent to the tight Miller geodesic going from our unstable foliation to our stable foliation. Okay. So, a maximal rectangle in our, well, a saddle connection, first of all, before I get to maximal rectangle, sorry. A saddle connection is just a geodesic arc connecting two singularities. So on the surface, I have a bunch of singularities of this foliation, and I can put a geodesic arc between these. It's a geodesic in the singular flat metric, and I get this saddle connection. And in some situations, I can make this maximal, or this rectangle that spans my saddle connection, and there won't be any other singularities within that rectangle. And so if that happens, that's a singularity-free rectangle. And then I'm going to get maximal rectangles by just pushing this singularity-free rectangle as far as it will go. I can either push it horizontally, or I can push it vertically as far as it will go. So in this picture, I push it horizontally, and eventually I hit singularities, and then I can't make it any larger. So this is a maximal rectangle. Okay. And so just a side note, since our map is a pseudo-Anosov, no leaf of our foliations can have a saddle connection. That is, there's no saddle connection between two singularities that lies along the leaf. All right. And so this means that our maximal rectangles are always going to have a single singularity on each side, and it's never going to be at a corner. Okay, so that's kind of important for what we're going to do next. So what we're going to do next is construct the veering triangulation, the layered veering triangulation, I should say. And so I should say this construction, the original construction of the veering triangulation, is due to Agol, and he had a very different construction. He used train tracks and splittings, if you know what those are. And this is actually the construction that is used in Mark Bell's program, Flipper, which he mentioned briefly earlier in the week. The construction that I'm going to show you is one by Garatow that he did, I think, in 2013 or so, using the quadratic differentials. So I have, well, I guess before I start, I need to puncture all of my singularities of my foliation so that I get more punctures on my surface. So I've changed my surface, so the mapping torus I get is actually going to have more cusps than if I just use my original surface. I can't get around that. I have to do that in order for this to work. So once I puncture all my singularities, now in my maximal rectangle I have a singularity on each edge, and I can just layer on this tetrahedron, which is going to have vertices at these singularities. So for every one of these maximal singularity-free rectangles, I can layer on one of these tetrahedra, with vertices at the 4 boundary punctures.
So how do you decide which edge goes over which?
So the edge with the greatest slope in absolute value is going to go on top. So this edge has a higher slope than this one in absolute value, so it's going to be the higher edge. You look.
That makes me. Oh, okay, fine. Yes, thank you. Right, so the edge that connects the top to the bottom always has slope between plus and minus 1. Going up
It's a square, yes.
Well, only I mean, that's because this is a square. Well,
they're always,
yeah.
yeah.
No.
Well, how do you
No,
know?
it's
No,
squares.
they're rectangle.
It could be. No, it wouldn't have to be a square.
So the one that connects the top to the bottom always wins.
No.
Yes. What?
Yes.
Yes, yes, it always wins.
You're right, good. And that might, okay, that's a comment to all, right, instead of mentioning stuff. Fine.
Okay. So I should remark here that really, when we do this construction, we should work in the universal cover of our punctured surface with the singular flat metric in the universal cover. I'm not really going to get into those details. It's kind of messy space, and for our purposes today, we can just imagine doing this on the actual surface, and I don't think it's going to be a problem, but just in case you're worried about that. Okay, so this is basically how we build it, and so let's see what happens when we start, if we just start with one and start sort of building out the triangulation, developing it out from a starting place. So this is a singularity-free rectangle. I have my tetrahedron on there, and so then I could try maybe, so this face is going to glue to another tetrahedron, which is going to be on the singularity-free rectangle, which is here, but then pushes upwards, because if I cut it here, there's no singularity above, so I can push it further up. So then I get this one, and then if I go further, I get another. Eventually, though, I'm going to have to go in a different direction. Right here, I can't go up anymore. I'm going to have to go down now if I want to layer on top. And so that one goes down, and then I'm going to layer one on the back face here, and then one more there. So I could keep doing this right here. On these last two, no, I'm layering them from underneath. Okay. So I could build this out in many directions, but really, really maybe it's better. I don't know if it's better, but like, really we're just taking all of the possible singularity-free rectangles we can make on this surface, and there are infinitely many, and we're just putting a tetrahedron in each one, and so the result is going to be that we're going to get, let me make sure I'm not getting ahead of myself. Yeah, so we get a triangulation T tilde of the infinite cyclic cover sigma naught cross R of our mapping torus M sub phi naught. So M sub phi naught is just the mapping torus we get from using our pseudo-Nosov restricted to the surface that we put more punctures into. Because we had to puncture it at the singularities. Okay, so now we have this triangulation T tilde of our infinite cyclic cover. And so the action of the monodromy's phi tilde lifted to this cover is simplicial with respect to our triangulation. And so the quotient is a triangulation of the mapping torus M sub phi naught. This is Garito, I guess that was 2015, not 13. This is Garito. And so a triangulation is a layered triangulation. So this just means that it's obtained by layering tetrahedra onto a surface, or at least that's one simple way of saying it. And it's a veering triangulation. So I haven't actually told you what veering even means. I just said, here's a construction, I'm going to call it veering. But I should probably tell you what that word means. So basically it means tetrahedra look like this, but I need to add a couple of decorations. So I get angle 0 angles here, and up here also, and angle pi edges here. So I'm going to think of this as having some sort of geometric structure where it's just a flat tetrahedron. And I have this cyclic ordering on the vertices, so it's counterclockwise looking down from the vertex. I get a red angle 0, and then a pi angle, and then a blue angle 0. So this is one way of characterizing the veering condition. Okay. So another way, with Garato's construction, an easy way to see that the triangulation has this structure on it is I can just say that my edges are going to be red if they have positive slope, and they're going to be blue if they have negative slope. If I just color all my edges like that, then it's gonna turn out to work. And I'm not gonna prove that, but it's not very hard to see if you just look at the pictures enough. So immediately I know how to color my edges in my triangulation with the construction that I showed you. Okay, and then there's also a third way of defining the veering condition, which is one that I like a lot. And this was Agol's original characterization of the condition from his paper. So faces attached to an edge veer right or left. And so if I have a blue edge, for example, then as I go up in my, so in my direction transverse to my fiber, I go up, my triangles that are attached to my blue edge veer to the left. So you can see this edge is above, so I'm going upwards out of the page, and my triangles are veering to the left. So if this edge were right, were red, then it would be the opposite. It would veer to the right. Okay, so it's just another way, and this is equivalent to this definition here by work of Hodgson, Rubinson, Segerman, and Tillman. Okay, so with this combinatorial condition, this coloring of the edges, I have two different types of tetrahedra. This is going to be important later. Some of my tetrahedra are called hinges, and this just means that my angle pi edges have opposite colors, so one's blue and one's red. And I may have situations where my angle pi edges both have the same color. If both are red or both are blue. So these are non-hinges, and the other tetrahinges, and some people call these fan tetrahedra. Both good words. So very roughly, a guiding principle here is that non-hinged tetrahedra, when you have a mapping class with, say, a power of a Dane twist in it, then what's going to happen is where you have that Dane twist, you're going to have a bunch of non-hinges layering around that annulus. And so in your triangulation, morally speaking, you're going to have a bunch of solid tori coming from layering non-hinges on the annuli, and then your hinges are going to be the glue that holds all of this together, roughly. Okay, so let's look at our layering process again now with in color. So now I've colored the edges according to the combinatorial condition, which was easy because I just looked at their slope, right, since I was able to characterize it that way. So this one is a hinge, and then I get a non-hinge, and I get a few non-hinges, and then hinge, and these last few are all hinges. And you can kind of see how when you have a non-hinge hinge following a hinge, it's kind of going in the same direction, and hinges sort of change direction in some sense. And then that last tetrahedron closes up all the tetrahedra around this edge. So hopefully this picture gives you some intuitive sense of this sort of difference between the hinges and non-hinges. Okay, so now that we hopefully have some understanding of what this triangulation is, let me give a little context. So as I said earlier, this was introduced by Agol in 2011. In 2013, a bunch of people, Hodgson, Rubinson, Segerman, and Tillman, and independently Futer and Garatow, showed that these triangulations emit positive angle structures, but they are not always geometric. And this was shown by Hodgson and Segerman in 2016. They found several examples of non-geometric veering triangulations, the smallest one having 13 tetrahedra. So that's unfortunate. So this was in response to a question of Agol in his paper. He asked if maybe these are always geometric. And the reason that was sort of a good question is that these are a generalization of triangulations of punctured tori and four punctured spheres, which are always geometric. In fact, they're canonical, the more specific version. So it was natural to ask maybe we have something to hope for, but it didn't pan out. So Garreteau in 2016 gave a new construction via quadratic differentials, and he also showed that the combinatorics of the veering triangulation are related to the Cannon-Thurston map in some way that I'm not at all going to go into. That's a very cool result. More recently, Minsky-Taylor showed that the subsurface distance between the singular lamination L, or the laminations L and LS and L mu, so this is the stable and unstable laminations associated to the foliations that I talked about earlier. So this subsurface distance is bounded in terms of the number of tetrahedra of T. So if that means something to you, then great. If not, I'm not going to really go into that further. And then between 2013 and 17, Mark Bell developed this program Flipper, which helps us actually construct veering triangulation. Excuse me. So, the first thing I'm going to talk about is experimental work, just using Flipper and building hundreds of thousands of these triangulations and see what kind of things we can learn. And so in order to do this, we need to have some notion of a random veering triangulation. And so the way we're going to do that is we're going to randomly sample pseudo-Nosov maps. So I have some generating set, and so these are my generators pictured there. And I'm going to take a simple random walk in its Cayley graph with respect to this generating set. And so if I do a random walk, then I get some element, and that element is going to be a pseudo-Nosov. Almost surely, if I take my words long enough, if I work a rivet and Mar, I'm pretty much definitely going to get a pseudo-Nosov. And so that gives me the foliations, and then I get the singular flat structure, and then I build my triangulation. And so then I construct the triangulation with Flipper, and for geometric information, I feed the results into Snap. And so this gets us back to our first question. Do we get any geometric information by looking at the combinatorial information of the veering triangulation? And so the first result I'm going to show you, so this is not the result. This is actually something to contrast it to.
Sorry, just show it fast on the previous slide. You were, oh, I see. Okay.
Yeah, so this is just harkening back to the question at the start. Okay, so what we're seeing here is actually, so Riven showed that generically volume is coarsely linear in the number of tetrahedra T. So this is known. So the x-axis here is the number of tetrahedra in my triangulation, and the y-axis is the volume of my triangulation, so the volume of the manifold. And you can see there's this linear relation, and so that was predicted by Riven, and sure enough it's there. These gray guys down here are non-generic. They're not obtained by random methods. They're obtained by sort of, so these are actually obtained by making sure that there's this really large power of a Dane twist in there somewhere. And that basically drives up the number of tetrahedra by layering on hinges around the annulus where I'm doing the Dane twisting, but it doesn't really drive up the volume much because I'm converging toward the manifold where I have that curve drilled out. And so I'm converging from below to some volume. So the volume is bounded at some point, but I can drive the number of tetrahedra up as much as I want. So in this picture, I can find outliers to this relation as bad as I want. Okay? But generically, this linear relation holds. So if I throw out all the hinge tetrahedra, though, then things look a lot nicer. So now I'm comparing, sorry, if I throw out the non-hinges, then things look nicer. So now I'm comparing the number of hinge tetrahedra in the triangulation to the volume. And so notice that, one, the linear relation is much, much better. And two, so all these outliers are still here. They're just in line here. I guess they're under other stuff, but they're no longer outliers. The reason for that is that, so as I said earlier, non-hinges, generally speaking, are layered onto annuli where you do a large power of a Dane twist. The way I constructed those outliers was to artificially insert a large power of a Dane twist. And all those tetrahedra that layered on from that process have been removed from, because they were all non-hinges. And I'm just counting hinges now. So I no longer have that issue.
How much do these colors overlap?
Sorry?
How much do these colors overlap? So for example, the picture suggests that the linear constants for green is different from the red, but it's
yes.
difficult to see
Yes,
because
yes.
they might overlap.
So I would have to look, but I would say the green and blue are probably not much wider than the yellow and not as wide as the blue. Or sorry, the green and red are probably not as wide as the blue one. Is that what you mean? Like how wide are
Well, I mean, like how many green dots are underneath the red dots, for instance? Or are they
quite a bit. I mean, I
difficult to tell from the picture.
Yeah. I mean, so if you go to the paper, there's like, it sort of breaks. I mean, this already, I have, the green is genus 0 and the number of punctures is varying. So in the paper, I have pictures where I'm separated by number of punctures, and you can see a much better breakdown of what's going on. I just didn't include all that here.
But it does look like there's maybe different constants for different.
Yes. It does look like as the genus is increasing, the slope of the relation is increasing a little bit. And so that's definitely one question that I'm curious about, and I don't know the answer. If that's so.
Was that the same behavior on the previous slide as well?
It's actually opposite on the previous slide,
Yeah.
right? So here the slope is going down as you. Yeah, so it does appear that the linear relation, the constant, depends a little bit on genus. So I have another slide which I didn't include where I take the sample in terms of genus and number of punctures, so like the sample in terms of the number of surfaces I look at. I extend that some, and it looks like what's happening is for a small complexity, it's for well, let me show you at the end. There'll probably be time. This talk tends to run a little short, so maybe I'll show you that at the end because it's going to be hard to explain.
So, can I ask you, maybe I'm ignorant, but how do you compute the volume? You have to solve all the equations to find out the structure and then feed into the volumes and add them all up?
Yeah, so I just give Snappy the triangulation, and it comes up with a solution. It may not be geometric. It may have negative tetrahedra, but the volume is still pretty much reliable. So I actually also ask it to retriangulate and try to find a geometric solution just to be safe. And for most of them it succeeds, and every single one that it succeeds on, the volume is basically the same. So that gives you some sense of how reliable Snappy is even for triangulations that aren't geometric. It'll still give you a good volume. Okay. So, as has come up already, the slope appears to depend on the surface. And so a lower bound, a universal lower bound, would follow from a conjecture of Casson, along with a result of, something that is contained in the paper of Futer and Garriteau that I mentioned earlier. So if you can prove this conjecture, which basically says that the angle structure has lower volume than the geometric structure, then you get a lower bound. The upper bound, I don't know, I don't have any ideas of how to prove that. There is an upper bound that exists that is a linear function of the Euler characteristic, so you don't get so this is Agol, Brock, Futer, Minsky, and Taylor. They have proved that these, so this is a universal lower bound, not anything about generic stuff or just absolute upper bound in terms of Euler characteristics. So this basically means for a fixed triangulation, T sub h divided by vol t is absolutely bounded in terms of the Euler characteristic of the surface.
How does that slope compare to these slopes?
Well, I'm pretty sure it's much bigger. I mean, I think, I don't know how it compares at this level, but I think it's going to be much bigger very quickly, because this is going to grow quickly, and this, according to what I've seen, is not growing very fast, and it looks like it might also be stabilizing. But I'll show you a picture that suggests that later, because I guess I should have put it in here earlier. But. All right. So this is one of the experimental results that I wanted to show you. Another one, so the other question that I talked about at the start, how frequently are these triangulations realized geometrically? So, as I said earlier, for the case of the once-punctured torus, if my surface is the once-punctured torus or the four-punctured sphere, then these are always geometric. This is a result of Akiyoshi, Lackenby, and Garitow independently. In fact, in these cases, these are canonical triangulations, if you know what that is. And so, as I also said, Hodgson, and Singerman gave the first examples of non-geometric triangulation. And in that paper, they said it's still somewhat of a mystery why varying triangulations are so frequently geometric. And I think the result you'll see next will kind of solve that mystery, maybe not officially, but in an experimental sense, which is that I think the problem is that they were looking at pseudo-Nosovs that were too small. Because if you make your pseudo-Nosov word very large, very quickly you get pretty much nothing, very little at all that's geometric. So in their paper they were looking at fairly small words, because they were looking at a census, they were looking at like a ball in the Cayley graph of the mapping class group and building out. And you can't really get much doing that because the ball just gets too big too fast. So you can't get very far before you're running out of the ability to compute things in a reasonable amount of time. And that's one of the reasons that random walks are a good way, work, because you can actually get large words and see other phenomena happen. So here this shows that, so this is broken up by the surface. This x-axis is the word length, and this is the fraction of the triangulations that ended up being geometric. And it looks like it decays exponentially, and in fact, if we graph it with a log axis with a log y-axis, then it looks linear, which suggests that it's exponential decay. Don't pay attention to this. The fraction here is so small that the sample size isn't big enough to really be reliable. So this is each of these dots is between 2,000 and 20,000 triangulations, depending on, down here we need a lot more to get it to stabilize. Up higher it stabilizes fairly quickly and you don't need as many. So this I could probably get to stabilize if I shot it up to like 100,000 maybe, but it's getting kind of crazy and at some point you have to let it go. But it definitely looks linear. And so, well, before I get to that, so for genus 0, notice that here I don't have any genus 0. And the reason is just that the decay rate is far different. And it would, if I put these on the same graph, it would just squish everything to the bottom for the other stuff. So here, it's decaying much slower, but again, it still looks linear whenever you plot it with a log on the y-axis, roughly. So I think it's likely that in both cases, we're getting exponential decay. And so that's a conjecture. For a surface with complexity greater than 2, obviously we don't want to count the punctured torus and the four-punctured sphere, because we know it's not true in that case. If p is the probability that a random walk of length k on a set of generators yields a geometric varying triangulation, then there exists some constant c so that this limit goes to 0. So that basically says this probability is decaying exponentially to 0. And so the theorem, which I'm going to show you an outline of the proof of, is that we get decay, but you can't say exponential. Can't prove exponential yet, but we do get decay to 0. So that's what I'm going to show you next. Okay, so just an outline. There'll be a lot of details pushed under the rug, but hopefully the outline will be enough to give you an idea of what's going on. So first we need a lemma. So for each surface that we're interested in, we need a pseudo-Nosov, and it's going to need to be in the principal stratum for reasons you'll see later. We need a pseudo-Nosov such that the associated varying triangulation is non-geometric. So this is sort of going to be a seed for each surface that I'm going to use to leverage my convergence, I guess. And so for that, we need to digress a little bit into something that Echo talked about a little bit the other day, which is the Thurston norm ball. So varying triangulations are somewhat rigid in that there are finitely many for any I should say layered triangulations. There are finitely many for any mapping torus. So a typical mapping torus fibers in infinitely many ways, and each of the fibers appears in a fibered face of the Thurston norm ball. Excuse me. So this is a convex polytope in second homology. And so this red face is supposed to be a fibered face of the ball. And so every integer homology class contained in an array passing through a face is a fiber of some, passing through a fibered face is a fiber of some fibration. So if I take any point here, if it's a, if out here somewhere there's an integer lattice point that is on the same array, and that's going to be a fiber for some fibration. And so as Echo mentioned, all fibrations on a face induce the same two-dimensional foliation of n. And with not too much work, this implies that the varying triangulation is an invariant of the fibered face. So on this face, I have all these different ways of triangulating my manifold M sub phi, all these different ways of fibering my manifold M sub phi, and they all have different fibers, so my surface is changing. So I have different surfaces here, but they all give me the same triangulation. Right? And so this, I guess this is just a picture of the two-dimensional foliation, again not showing up very well. And so the upshot of this is if one fibration has non-geometric varying triangulation, then so do all the other ones. So if I can find, from this lemma up here, one surface that has a non-geometric varying triangulation, and it's in some face, and then every other surface that's a fiber in that face also has some non-geometric varying triangulation associated to it. So that's how I'm going to prove the lemma up here, is to leverage this fact here. And so basically what we do is we find fibered faces explicitly containing lots of fibers. And we can't do it all in one face, but we don't need that many. So first we find a face containing fibers sigma 1n for all n greater than or equal to 2, and which also has a varying triangulation that's non-geometric, and its monodromy is in the principal stratum. And we find a face containing all the fibers of genus greater than or equal to 2, and all of the punctured spheres with 7 or greater punctures. And then for 5 and 6 punctured sphere, we just have to do those individually. And then closed surfaces we take care of using covering tricks. We just need to find a triangulation on sigma 2, 0, and then since every other closed surface covers sigma 2, 0, we can just lift it upstairs and it's still going to be non-geometric. So we get those that way. Okay. And so to find these, so we actually need to find examples for each one of these, right, to build off of. So these are all found partially using Regina to figure out what the Thurston norm ball is going to be and to analyze that.
How many tetrahedra you have in your faces?
So these base cases, I think, have around 35 tetrahedra typically.
That's a lot.
Yeah, wow.
Well, I mean, sure, it's a lot, but I mean, most of the triangulation that you've seen from the data have like hundreds of thousands of tetrahedra. Sure. So, I don't know, after doing all this, I feel like 35 is pretty manageable. Anyway.
So can you find all, for 2, can you find all pairs Gn? G is greater than 2n?
Yes,
Not
yes,
all
yes.
at one, or one.
Yes, so this 2 takes care of a lot, right? So yeah, so there is some face that has all these fibers in it. Okay, so that gives us the lemma. And then so we use this theorem of Godler and Marr that says if I have a mapping class which has a quadratic differential in the principal stratum of Teichmüller space, so this just means that its invariant foliations are generic in the sense that all of my singularities are 3-pronged and all of my punctures are 1-pronged. Okay, so that's basically what the principal stratum means. And omega sub n is a bi-infinite simple random walk on mapping class group. Then there exists some rho such that for any d, this gamma sub omega n, which is the Teichmüller geodesic for omega n, is going to rho fellow travel with the translate of gamma sub g. So gamma sub g is the Teichmüller geodesic for g that I started with for a distance d if n is sufficiently large. So basically, if I go far enough out, if my random word is large enough, then the Teichmüller geodesic for that word is going to be close to the Teichmüller geodesic g that I care about. So this g is going to come from this lemma up here. This is going to be my guy that I know has a non-geometric veering triangulation. Okay. And so actually, I have to translate it actually, because I want sort of a base point. I want it all to stick near that base point. But that's okay, because translation is just conjugation, and that's not a problem. Okay, so this theorem implies that so Qn is the quadratic differential associated to my random word at step n, and then Q is the quadratic differential associated to G. So this implies that Qn converges to Q in Teichmüller space. So I have my gamma sub G, and I have gamma sub n, or omega n, which, so I have some base point here, which gets close to G. If I can make how close it gets be more by just making my n larger, and so that's going to force my quadratic differential, which is basically, you can think of as a vector here, that's going to converge to this quadratic differential. So this is Q, and this is Q sub n. Sorry for the small writing. And so I get quadratic differentials converging, and then, oh, that was premature, but oh well. And then so my quadratic differentials after puncturing, so this is lifted to the Teichmüller space of the punctured surface. So these also converge. It's not too hard to show. And then so I need a lemma that says, if I get convergence of these quadratic differentials in my punctured Teichmüller space, then my veering triangulations in my infinite cyclic cover converge. Sorry, it looks like I changed the notation for the veering triangulation. It's tau now. So this convergence is a based convergence. So it's based at edges edges of the triangulation that are less than some fixed length. So the convergence is happening around this part of the triangulation where my edges are bounded in length.
So this is the length in the quadratic differential?
Yeah, in the singular flat metric. Yeah. So basically, what this says is, so I guess I should say, and it follows from what I said earlier, but maybe it's not obvious, that the edges of my veering triangulation are exactly saddle connections that span singularity-free rectangles. So this is my foliations. So this is basically saying, if I perturb my quadratic differential a little bit, then this edge is not going to change. If I perturb it, then the triangulation I get after this perturbation is going to be the same, as long as I'm not dealing with any extremely long edges, because extremely long edges could be coming from these like really, really skinny rectangles that are a little more sensitive to perturbation. Okay, so I get convergence of my veering triangulations and the infinite cyclic cover. And then, so I guess I should say, so this is based at edges of bounded length. So eventually I get convergence on some fundamental domain. And then that's enough, because I'm really concerned about the triangulation in the mapping torus downstairs. And so then I apply a theorem of Leininger and Schleimer that says there exists a homeomorphism between, so this is the doubly degenerate representations of my punctured torus group, the fundamental group of my punctured, sorry, not punctured torus, punctured surface. And this is ND laminations on my punctured surface cross ND laminations modulo the diagonal. So this is basically my foliations of my quadratic differential. And so I have a map from quadratic differentials on my punctured surface to here. Just take a quadratic differential and look at its foliations. And then so I get a map from here to here because this one's a homeomorphism. And this is obviously a continuous map. So I get a continuous map from here to here, so I can push my convergence from my quadratic differentials to my representation, my representations. Okay. Of my fundamental group. So this is, I guess, one reason that I want to be working in the infinite cycle cover, because I want to work with the fundamental group of my surface. So this convergence right here gives me convergence of parabolic fixed points corresponding to the vertices of the negatively oriented tetrahedron. So I have some special negatively oriented tetrahedron. So if I look at it in the universal cover, page 2. And so I have these parabolic fixed points. And so my convergence of my representation tells me that if I'm careful, that I can pick these parabolic fixed points to converge. And then so eventually, if my limiting tetrahedron is inside out, then my random word tetrahedron are also. So I get a negative tetrahedron. For n large enough, my triangulation is going to have a negative tetrahedron coming from that. Okay. All right, so that's the proof. So I guess there's one other thing that I wanted to talk about, which is the third question. So now we know that these triangulations are generically non-geometric, which is sad, because I like geometric things, but it's true, so we can't help it. But maybe we can still find infinite families of geometric triangulations, veering triangulations. So this is one possible such family, or actually two families. These are two different families. So this one is on the twice punctured torus. And so I have this well, let me tell you what these generators are, because you probably forgot from the picture before. So two punctures, and then I have A naught is this, and then B naught is going to be this, and then B naught is going to be using colors. This is B naught. So I do a large power of A naught, B naught inverse, and then I do one P naught to make it a pseudo-Nosov. If I didn't do something else, then it would be a pseudo-Nosov. So basically, morally, the idea here is that this A naught, B naught inverse map is happening on a subsurface, the subsurface of punctured torus, and it's the monodromy of the figure 8, which has a geometric veering triangulation. So the idea is to make most of the stuff that's happening hopefully have geometry similar to the figure 8, and then just do something at the end and hope that it doesn't screw things up too much. And as it happens, you get lucky. And so these blue dots are, so the blue dot is the thinnest tetrahedron in the triangulation. So this axis is telling you the imaginary part of your shape parameter. Remember I said your tetrahedron is negative if your imaginary part is negative. So this is saying that all the imaginary parts are positive, although they're getting very small, obviously. This is down to 10 to the negative 10 at this point. But it's still positive, and this is the smallest one. And the convergence is very, very regular. And so the hope would be that it's converging to 0, but always positive for finite k. So by the way, this is computed in Snappy with high precision. So as long as you trust Snappy, so this is 60 decimals or something like this. And so for 60 decimals, this is a pretty large number, I guess. And so this is maybe, this is not verified. You can't verify things this big in Snappy. These are way too, probably have at this point thousands of tetrahedron. But, and so this is another example that basically works with the same sort of idea, but now it's now you take two subsurfaces that look like a punctured torus, and then do something to tie them together to make it a pseudo-Nosov, and hope you get lucky. So I think it's pretty likely that you can generalize this construction to larger genus. Just do the same type of thing, and so you have G punctured torus subsurfaces where you do this, and then you tie them together. So maybe you can get infinitely many of these families, but these are the only two I've checked.
So have you thought about how to control edge degrees? Because if the degree of some edge becomes very large, then you expect to see very small volume tetrahedron. But if you could bound all the edge degrees from above, could you?
He's cranking up the edge degree.
I know,
Yeah.
and that's why I'm wondering. Could you try to come up with constructions where you have universal bound in the edge degree, and that way maybe you get you stop your tetrahedron becoming
I see.
tiny.
No, I haven't thought of that, but that's a good idea. So you're saying this would be another way maybe of constructing a family like this and try to figure out a way to...
I guess you get some bound on. I mean, there are these examples, right? This poison pattern. Yeah, right. So the degree, edge degree there would you'd have to be working with an edges that are less than whatever appears in those.
Yeah.
All right, that's it.
In the twice punctured torus, there's some version of the Berman kernel, which is these sort of generate these double Dane twists. And there's sort of two of them which generate, and they're actually a free group, as they have to be. I think that Futer and Garriteau had some reason to think those might all be nice-ish.
Well, he hasn't told me.
Well, so you might ask your advisor.
Yeah, that's a good question.
They seem interested in those over time, so that's an interesting